Okay, so eventually some of these results were improved. There were still some discrepancies, okay? And some discrepancy, improvement was made. Or improvements were made by considering elliptical orbits. Okay, because in some sense they take into account classically kind of the orbital angular momentum, the degeneracies. And the other thing was, of course, the real success came through applying Schrodinger equation, which is what we're going to do today. So Schrodinger equation gives you, it doesn't require you to assume non-radiating, orbits. You don't have to have a classical picture in the Schrodinger equation, right? In the Schrodinger equation, all these things are, there is really no classical rotation, so there is no need for classical electromagnetic radiation coming out. And then, even then, there are discrepancies because, if we apply the Schrodinger equation naively, which is what we will do today, what are we ignoring?
The potential?
No, we will use the spherical symmetric potential. But if you only take into account the spherical symmetric potential, we are still ignoring some stuff. What is it that we're ignoring? What aspect of the electron and the proton are we ignoring if we just take into account the spherically symmetric potential?
Their charges?
The potential is the Coulombic.
Right.
So we are taking into account the charge.
Yeah, I'm out of ideas then.
Rahul?
Sir, I'm actually having a lot of net issues. আমার অনেক ভেঙে যাচ্ছে কথা।
Okay, Moon just left. Okay, maybe I shouldn't have asked her the question. Wajiha, do you have any idea? What do you think? Is there any degree of freedom that the electron has that is not described by?
So could you repeat the question?
If I consider the attraction between an electron and a proton, if I describe that by a spherically symmetric Coulomb potential, so let me write the equation. So the Schrodinger equation is going to be, P squared by 2m acting on psi plus V of r psi equal to E of psi, where V of r is, say, in the CGS system, we're going to take the CGS system, is an attractive potential. It's minus E squared divided by r. Okay, so what I'm trying to say, what I'm asking is that, what aspect of the electron and the proton, is missing from the Schrodinger equation, that from this equation that we should take into account for a more accurate experimental, for a more accurate agreement with the experiment. So let me ask you a related question. So okay, why don't you think about it, and then we'll see if somebody guesses the answer. What aspect of the electron and the proton is missing from this equation? If psi is just some wave function, right? Psi is just a function of x. x. Like, of course, we are looking at the time-independent Schrodinger equation. That's not a big deal because we can always find the time-dependent by evolving it. But there's something else that's missing. So let me ask you a related question. What kind of particles are electrons and protons?
Electrons are fermions. And protons are bosons, I think.
Are what,
Or-
bosons?
I'm
No.
probably forgetting something.
Protons are not bosons. Protons are also fermions.
Oh, okay, so both are fermions.
Yeah. So what is a fermion? Can you tell me?
All right, so that like both can't have the same state. Two particles can't have the same state. That thing?
Yeah, but that's a result of something.
Yeah.
I think spin.
Yes, they both have. So spin what?
Half spin.
Half spin.
Electrons
They
have
both
half
have
spin.
spin half, right? But-
Do we know the spin of proton? Like
Yeah, of course we do. Spin
a
half.
half, okay. Like I was googling something about proton, and it says that we don't know the exact spin of protons, and that felt weird to me. So
That's probably not true. You probably must have gone to some COVID misinformation, proton information site.
yeah, probably.
Go to Wikipedia. Wikipedia is a good resource. Wikipedia doesn't lie usually.
Yeah.
It's not the Quran, so you're not going to get God's truth, but Wikipedia comes as close to human truth as is currently possible. Okay.
Yeah, definitely.
Okay, so protons have spin half, electrons have spin half. Does this equation have a spin degree of freedom? If I'm looking at this as a...
I don't think it does. It doesn't have that.
Right. So it's because if you were to see that, a spin half particle, its spinner, its wave function is not just a function of space-time, it's also a function of its spin degrees of freedom. So we need to replace, if we have a spin half particle, so suppose this is a spin half particle, we need to replace this by a spin vector. Let me not use this notation because the spin vector is in a different, it's basically going to be a it's going to be a two-dimensional wave function, okay? And that's not what we are saying that, oh, this is just an ordinary wave function. So this is to say that, to get more closer to the, to get more accurate, agreement, with experiment, we have to take into account spin. In general, in principle, we have to take into account spin orbit coupling. So what is spin orbit coupling? So orbital angular momentum is integer, right? Do you remember that?
So could you repeat that again?
Orbital angular momentum is always integer.
Yeah.
Okay. But spin angular momentum, if it's spin half, then they're going to have half integer value. So we have to, consider tensor product like this, or tensor product like, this. And then we have to do the Clebsch-Gordon stuff, right? This is exactly what we did earlier today, but we were doing half cross half, right? But you have in your assignment something like this. So that analysis becomes important here. When we have to do like, the coupling between spin and orbit is, and of course there's also going to be spin-spin coupling, right? Because there will be some interaction between the proton and the electron spin as well. Although it'll be very, very like a higher order effect. And it turns out all of this is not enough. Even then, there are these subtle discrepancy from, from experiment, and there is a shift in some of the very slight shift in some of the energy levels known as the Lamb shift. And to explain the Lamb shift, quantum mechanics is not enough. You have to take into account that particles interact with each other, and the vacuum around them through virtual particles. So you need, and quantum mechanics isn't powerful enough, you need quantum field theory and very sophisticated quantum field theory to be able to explain Lamb shift, okay? So even to explain the hydrogen atom, the amount of mathematical and physical sophistication that you need is just mind-boggling, okay? Quantum field theory is a subject that cannot be, to my knowledge, to my understanding, cannot be taught satisfactorily at an undergraduate level. That is not to say that I don't know, that is not to say that I don't know undergraduates who know quantum field theory really well. There are. But it's not practice to teach quantum field theory at an undergraduate level. Okay, so this is my spiel. Any questions before we actually go into the solving the Schrodinger equation?
Sir, can we repeat the same thing with things other than bosons, other than fermions? Like bosons or Higgs boson or other particles?
Same what?
The Schrodinger equation, like the thing that we just talked about.
Yeah, for example, particles such as, well, there's some problem. The problem is that so all quantum mechanical particles obey the Schrodinger equation. Mm-hmm. But it's kind of a bit of a generalized version of the Schrodinger equation. But the Schrodinger equation is as we understand it in this course, is a non-relativistic equation, okay? So particles, there are particles, most in quantum field theory, such as the bosons, and which are, they are relativistic, meaning that, to create them, you need very, very high energies. So once you create them, they will have very high speed, and, you will have to take into account relativistic effects. And Schrodinger equation is not good enough for that, okay? Schrodinger equation doesn't know about relativity. That's number one. That's number 1 point. Number 2 point is that Schrodinger equation, it's very hard to build into it the evanescence of particles, right? For example, photons, right? Photons are particles which do not have any charge. So photons can be absorbed, it can be emitted. The total number of photons in an experiment is not conserved. But Schrodinger equation, as we know, has a hard time dealing with particles which can appear and disappear out of nowhere. Okay, so for that, you actually, the better framework is quantum field theory. That's exactly why quantum field theory was invented, because it can deal with situation where particles, or let's say excitations, and it can be a particle, it can be a pseudo particle, it can be it can be something which looks like a particle at a certain energy level, energy scale, but at a higher energy scale is actually not a particle. Those things, it's easier to deal with using quantum field theory. So it would not be advisable to actually use the Schrodinger equation to say work on the Higgs boson. But on the other hand, if you take an atom which is a boson, say some chemistry experiment where there are atoms which have spin such, all the constituents have spin such that the lowest energy level that they're in is where the combined spin is 0. For those cases, we have something which is more or less stable. It can, of course, lose a charge, which is fine. That would be very comfortably described by quantum mechanics. Okay, so quantum mechanics is good for low energy, non-relativistic stuff, such as chemistry, but it is not, Schrodinger equation, but Schrodinger equation is not a good way of dealing with very high energy relativistic stuff, okay? Even like low energy stuff, such as, say, suppose you are dealing with a huge, like a, I don't know, n, where n is very large, particle system, right? So if you want to write down the Schrodinger equation, the wave function there is going to be a function of too many variables for you to be able to solve in any satisfactory manner. So you can write down the Schrodinger equation in principle, but it's not going to do you any good whatsoever. In that situation, we go to statistical mechanics. Or we can even go to non-relativistic quantum field theories. So for example, lattices, can have, condensed matter systems can have excitations which are essentially, quantum versions of sound waves in matter, and they are known as phonons. And phonons act like pseudoparticles. Sorry. Okay, and those phonons can be, the interaction of phonons in a continuous system can be described by non-relativistic quantum field theory, for example. Okay, that's a very qualitative answer to a qualitative question. Okay.
Yeah. Okay. Thank you, sir. Got it.
Okay. So any other questions before we delve into the Schrodinger equation?